Hello, in this lesson we're going to study one of the most important ideas in all of trigonometry, the unit circle. The unit circle helps us define the trigonometric functions, evaluate them at important angles, and understand patterns that will appear again and again throughout pre-calculus and calculus. Our goals in this section are the following. First, we want to understand what the unit circle is and how it relates to real numbers. Next, we will use a unit circle to define sine, cosine, tangent, and the reciprocal functions. Then, we will evaluate trig functions at standard angles without a calculator using exact values. We will also study important patterns such as periodicity and symmetry, which help us simplify trig expressions and evaluate functions more efficiently. And finally, when exact values are not available, we will use a calculator appropriately. So this lesson moves from geometry to function definitions to evaluation and properties. Let's begin with the definition. The unit circle is a circle centered at the origin with radius 1. Every point xy on this circle satisfies the equation x squared plus y squared equals 1, because that is the equation of a circle of radius 1 centered at the origin. Now, why do we use a radius of 1? Because it simplifies everything beautifully. Recall the arc length formula, S equals r theta. If the radius is 1, then this becomes S equals theta. So on the unit circle, the arc length and the angle measure in radians are numerically the same. That means that a real number t can be interpreted both as an angle in radians and as a distance traveled along the circle from the point 0, 1. This slide helps us connect the real number line to the unit circle. A useful way to picture this is to imagine the real number line as a flexible tape wrapped around the circle, beginning at the point 1, 0. If t is positive, we move counterclockwise. If t is negative, we move clockwise. So when t equals 0, we are at 1, 0. When t equals pi over 2, we arrive at 0, 1. And when t equals pi, we arrive at negative 1, 0. And when t equals 2 pi, we have gone all the way around and return to 1, 0. This is why values that differ by 2 pi land at the same point. This slide asks why t equals pi over 4 and t equals 9 pi over 4 correspond to the same point. The reason is that 9 pi over 4 is the same as pi over 4 plus 2 pi. So starting at pi over 4 and then adding 2 pi means making one complete revolution and returning to the same location. More generally, any 2 points that differ by a multiple of 2 pi correspond to the same point on the unit circle. Now we come to one of the most important slides in this lesson. Let t be any real number and let x, y be the corresponding point on the unit circle. Then the trigonometric functions are defined as follows. Cosine t is equal to x, sine t is equal to y, and tan t is equal to y over x when x is not equal to 0. And the reciprocal functions are cosecant t is equal to 1 over y when y is not equal to 0, secant t is 1 over x when x is not equal to 0, and cotangent t is x over y when y is not equal to 0. The most important fact here is this. Cosine is the x-coordinate and sine is the y-coordinate. Everything else is built from that. Tangent is the ratio y over x, so it can also be interpreted as the slope of the line from the origin to the point xy. That is why tangent is undefined when x equals 0, the vertical line. And the reciprocal functions are exactly what their name suggests, reciprocals of sine, cosine, and tangent. Now let's use the coordinate definitions to determine the signs of the trig functions in each quadrant. You may also know the mnemonic, all students take calculus. In quadrant 1, all trig functions are positive. In quadrant 2, only sine and cosecant are positive. In quadrant 3, only tangent and cotangent are positive. In quadrant 4, only cosine and secant are positive. But it is even better to understand why. Since cosine is the x-coordinate and sine is the y-coordinate, in quadrant 1, both x and y are positive. In quadrant 2, x is negative and y is positive. In quadrant 3, both are negative. And in quadrant 4, x is positive and y is negative. So the sign chart follows directly from the coordinates. This slide gives the coordinates for the pi over 4 family. At t equals pi over 4, the point is square root of 2 over 2, comma, square root of 2 over 2. Because this angle lies on the line y equals x, the two coordinates must be equal. And since the point lies on the unit circle, each coordinate must be plus or minus square root of 2 over 2. The other 3 points in this family have the same absolute values, and the only signs change depending on the quadrant. So once we know the first quadrant point, the others follow by symmetry. Now we look at the other major standard angle families, pi over 6 and pi over 3. At t equals pi over 6, the point is square root of 3 over 2, comma, 1/2. And at t equals pi over 3, the point is 1/2, comma, square root of 3 over 2. A very useful pattern appears here. At the smaller angle, pi over 6, the x-coordinate is larger and the y-coordinate is smaller. And at the larger angle, pi over 3, they switch. As the angle increases, the point moves upward and to the left, so y increases and x decreases. Again, the same absolute values appear in other quadrants, and only the signs change. This is a very important summary slide. Almost the entire unit circle can be built from just 3 first quadrant reference angles, pi over 6, pi over 4, and pi over 3, and their coordinates, square root of 3 over 2, comma, 1/2, square root of 2 over 2, comma, square root of 2 over 2, and 1/2, comma, square root of 3 over 2. So the strategy is, first, identify the reference angle, second, recall the first quadrant coordinates, and third, adjust the signs based on the quadrant. This is much better than trying to memorize every point separately. This slide asks when tangent is undefined between 0 and 2 pi. Since tangent of t is equal to y over x, tangent is undefined whenever x is 0. That happens at t equals pi over 2 and t equals 3 pi over 2 because these points are 0, 1 and 0, -1. Geometrically, those correspond to vertical lines, and vertical lines do not have a defined slope. Now let's apply the definitions. At t equals pi over 3, the point on the circle, on the unit circle, is 1/2, comma, square root of 3 over 2. So immediately, cosine of pi over 3 is equal to 1/2, and sine of pi over 3 is square root of 3 over 2. Then tangent of pi over 3 is equal to y over x, which is the same thing as square root of 3 divided by 2 divided by 1/2, which is equal to square root of 3. And then we use reciprocals for the remaining 3 functions. So this example shows the full process. Find the point, read off cosine and sine, compute tangent as a ratio, and get the reciprocal functions from there. Now consider t equals 7 pi over 4. This lies in quadrant 4, and the corresponding point is square root of 2 over 2, comma, negative square root of 2 over 2. So sine, which is the y-coordinate, is negative. Sine 7 pi over 4 is equal to negative square root of 2 over 2. And cosine, which is the x-coordinate, is positive. Cosine of 7 pi over 4 is equal to square root of 2 over 2. And tangent of 7 pi over 4 is equal to -1. This is also a good moment to check signs using the quadrant. Now let's evaluate the trig functions at the quadrantal angle t equals 3 pi over 2. The point is 0, negative 1. So cosine of 3 pi over 2 is equal to 0, and sine of 3 pi over 2 is equal to negative 1. Tangent is undefined because it would require dividing by 0. Secant is also undefined because secant is 1 over x, and here x is equal to 0. This example is important because it shows exactly where undefined values come from. Now let's evaluate trig functions at a negative angle. A negative angle means we travel clockwise from 1, 0. For t equals negative pi over 6, we move clockwise by 5 pi over 6, which places us in quadrant 3. The reference angle is pi over 6, so the absolute coordinate values are square root of 3 over 2, 1/2. But in quadrant 3, both coordinates are negative, so the point is negative square root of 3 over 2, negative 1/2. From there, we read off sine and cosine and compute tangent as usual. Now let's think of sine and cosine as functions. Since every real number t can be wrapped around the circle, sine and cosine are defined for all real numbers. So their domain is all real numbers. Their range, however, is limited. Because the x and y coordinates on the unit circle are always between negative 1 and 1, we have negative 1, we have sine of t is between negative 1 and 1, and cosine of t is also between negative 1 and 1. So sine and cosine can never be greater than 1 in magnitude. That is why something like sine of t is equal to 2 is impossible. A function is called periodic if it repeats its values at regular intervals. Since one full revolution around the unit circle is 2 pi, sine and cosine repeat every 2 pi. So sine of t plus 2 pi is equal to sine of t, and cosine of t plus 2 pi is equal to cosine t. More generally, adding any integer multiple of 2 pi brings us back to the same point on the circle. So the period of both sine and cosine is 2 pi. These examples show how periodicity helps simplify unusual angles. For example, if an angle differs from a familiar angle by a multiple of 2 pi, then sine and cosine have the same value. So instead of working directly with a large angle like 17 pi over 4, we subtract full revolutions until we land on a standard angle such as pi over 4. That gives us the exact value much more easily. The same idea works for negative angles as well. We add or subtract multiples of 2 pi until the angle is easier to interpret on the unit circle. This slide introduces symmetry. Cosine is an even function, which means that cosine of negative t is equal to cosine of t. And sine is an odd function, which means that sine of negative t is equal to negative sine of t. The same pattern applies to the reciprocal functions. Secant is even, while cosecant, tangent, and cotangent are odd. These identities are extremely useful because they let us evaluate trig functions at negative angles quickly, without recomputing everything. Since sine of t is equal to 0.6, then what is sine of negative t? Well, since sine is an odd function, sine of negative t is the same thing as negative sine of t, which is equal to negative 0.6. This is a quick application of symmetry. If sine of t is equal to 1/2, then t must be in a quadrant where sine is positive. Since sine is a y-coordinate, this means quadrant 1 or quadrant 2. The reference angle is pi over 6. So the two solutions between 0 and 2 pi are pi over 6 and 5 pi over 6. This is the beginning of solving trigonometric equations using the unit circle. Not every trig function comes from a standard angle, so sometimes we need a calculator. The most important rule is to check whether the calculator is in radian mode or in degree mode. Since this section is working primarily in radians, the calculator should usually be in radian mode. Also remember that reciprocal functions are often computed manually. For example, to find secant, calculate 1 over cosine of t. Here are some common mistakes to watch out for. One is mixing up sine and cosine. Remember, sine is y, cosine is x. Another is using the wrong calculator mode. And a third is trying to memorize too many isolated facts instead of using structure. A better strategy is to learn the first 3 quadrant coordinate families, use quadrant signs carefully, and connect every trig value to a point on the unit circle. To finish, work through these practice problems on this slide carefully. The goal is not just to get answers, but to connect each answer to a point on the unit circle. That is the central idea of the whole lesson. If you know the point on the circle, then you know sine and cosine immediately, and from there you can build the other trig functions. Once that connection becomes natural, the unit circle becomes much more logical and much less about memorization. Thank you, and I'll see you in the next lesson.